Good morning, everyone. Welcome to another webinar Wednesday with Softcrylic. My name is Sammy Anderson. I'm our marketing coordinator here. Today, I'm joined by our Director of Visual Analytics, Corey Turner, and one of our data scientists, Sam Steyer. They're going to go over everything about data models that you're going to have to know. If you have any questions throughout the webinar, feel free to throw it in our Q&A. We also have a poll up, so make sure that you vote on the different questions. And if you have any questions about Softcrylic or want to learn more or inquire about our services, always feel free to reach out, info@softcrylic.com. With that, I'll pass things off to Corey, and you can get going.
Good morning, everybody. Thank you for joining us. My name's Corey Turner, and I lead the Data Viz department or practice at Softcrylic. With me today is Sam Steyer, and I will let him introduce himself. Sam, go ahead and tell us a little bit about what you do at Softcrylic.
Sure. Hey, everybody. First off, I just want to thank everybody who's able to attend today's webinar with Corey and I. As Corey alluded to, I'm a data scientist here at Softcrylic. I work with clients both to help in support of their analytics goals or statistical modeling or machine learning, as well as even some of like their data modeling problems that they may face and need help in terms of coming up with a solution for. So we get to really work with a wide range of problems here as a data scientist at Softcrylic. So hopefully I can aid in Corey's effort to show everybody what the ideal data model is today.
Thanks, Sam. You know, as I was thinking about this, kicking off, data science and data viz, these two practices at Softcrylic are probably two of the closest in terms of working sort of hand in hand. There's often that we're asked to visualize some of the sort of spectacular data science that that Sam and his team puts together. And so we certainly have a great deal of sort of cross-practice synergy at Softcrylic across all our practices. I'm actually going to share with you guys a link to a video that we put together earlier in the summer that sort of talks about sort of cross-practice opportunities that we sort of share across practice leads. But with regards to data science and data viz, we're probably sort of the two of the tightest practices that we have. And so as a result, we kind of put a lot of thought into developing data pipelines that sort of work hand in hand with both practices. And so that's a good segue into what we're going to talk about today in terms of developing and producing data models that work really for both of our purposes.
Yeah, absolutely.
So as we start to dive in today, really this is sort of the agenda. As we talk about visualizing our supermodel, we're going to talk about supermodels and you, about what are the sort of the qualities of a data model. We've got three data schemas that we're going to really sort of unpack today: star schema, Snowflake, and then sort of a denormalized schema. And then we're going to dive further into just sort of what best practices look like for with regards to reporting on the Power Platform, and specifically sort of given its more advanced data modeling capabilities, and what sort of the best practices look for there, particularly with regards to developing a star schema. And afterwards, we definitely want to take any of your questions and discuss those. If there's anything that sort of comes up that's that's sort of immediate during the chat, Sam, please flag me and we can sidebar there. But otherwise, we'll hold everything to the end. We've got a couple of other upcoming events that we want to make sure you guys know about, and then we'll share some links for further reading and next steps. All right, so this is Derek Zoolander. And if you don't know Derek Zoolander is a supermodel, and he doesn't read good or other good stuff either. So the point here is, look, you don't need to be like Zoolander. After all, there's more to life than being really, really ridiculously good looking. But your data model maybe can be a supermodel where your business requirements are concerned. And really, this is all sort of driven by the idea that we're progressing toward this era of self-service BI and self-service data. And as we head in that direction, as we track towards that goal, the deliveries of BI departments, data science departments, analytics departments, any team really needs to become architecturally relevant in their ability to provide these solutions. And these solutions are not just to the current requirements of the business or to the specific business question that we're asking right at this second, but that really in their architectural relevance, they need to be relevant to the future questions that the business doesn't yet know how to ask, which is a tall order, but with a little bit of forethought, we can head in that direction. So, another movie reference here. I don't know how many of you guys know Weird Science. I didn't realize I'm dating myself, but you can't, in my mind, you can't talk about data nerds and supermodels without at least one Weird Science reference. So raw data comes in many shapes. On first glance, the data we have might not look anything like what we're hoping it might look like, or like our business requirements. But we have far better tools, and not to mention much better science than Robert Downey Jr. and Anthony Michael Hall had back in the 80s in Weird Science. But with these cutting edge tool sets that we have now, a little work and some creativity on your part and our part, we can create a data model that is beautiful, flexible, and powerful, and limited really by only our vision of what that model needs to do. All right. For those of you that don't know Weird Science, it's a very 80s movie about two very nerdy high school kids who managed to somehow create the woman of their dreams via some really ridiculous technology, and then how that ends up completely transforming the rest of their high school experience. We end up joking about it quite a bit, but it's a very 80s movie. And going back and looking at it, it's very obvious that the 80s were a very different time than 2020. But anyway.
I'm definitely gonna have to go check it out, Corey. This was something I was not familiar with. So,
oh, really?
Yeah, I was actually kind of shocked when I saw Robert Downey Jr. there, so young. I was like, whoa, that's Iron Man.
You definitely need to check it out. You and that's like you and the rest of the team, man. I realize I'm dating myself, but goodness gracious. So look, when we talk about data models, we're going to talk about a bunch of different schemas here. But with regards to any data model, our requirements are always going to involve two different types of information. And you guys know this already, but it's worth calling out that, dimensions are going to be the descriptive information about the entities, the things that we're modeling. Entities can be products, people, places, concepts, including time itself. In fact, the most consistent dimension you're going to find across all the data you work with is always going to be date and maybe time. In contrast, facts are where we store observations or events, and these can be things like sales orders, stock balances, exchange rates, clicks, impressions, temperatures, etc. Dimension, and then the interesting thing about understanding the dimensionality of your data is that the columns that you have for dimensions will determine the dimensionality of the data. But knowing the dimensionality of your data is not going to tell you the granularity of the data. In order to understand the granularity of the data, you need to look at the distinct values in those dimensional rows. For a good example here is with date. You're going to have a date column, but until you start looking at the values in that date column, you don't know whether you've got daily data or whether you've got weekly or whether you've got monthly or annual or whatever. So
totally.
That's
yeah, and Corey, I think a great example for people who come from like a online analytics background is to think about dimensions in terms of like that could be like day, visitor ID, session ID, and then facts as page views, time on site, and other things that are kind of describing their behavior during that day for that visitor and for that session.
Awesome. Thanks, Sam. Appreciate it. With that said, so we said we're going to talk about our three data models today. So again, some references that may be, hopefully you guys got these ones, but Molly Shannon in Superstar, she's our star schema. Got some Instagram influencer doing some cosplay here as Elsa from Frozen for our Snowflake. And then we've got Mugatu from Zoolander as our denormalization. If I didn't hit it with Mugatu, I don't know, Sam. Can you think of somebody else I should have done better for denormalization?
No, I thought that was an excellent choice. But I do think the first, I know she's a superstar in the front, but I think she could have done well for denormalization as well.
I think you're absolutely right. Absolutely right. Okay. So as we diving right in, when we talk about our data models, we're going to start with star schema because, and Sam and I went back and forth on this one. Should Snowflake start first, or should star schema start first? And I think Sam was campaigning for Snowflake first, but in the end, in terms of presentation here, I wanted to start here. So star schema is a very mature modeling approach. It's not like we invented it. It's not like this is new. You guys, many of you, if you're doing any data modeling at all already, you've worked with this already. And it requires us, as we were talking earlier, to classify not just the various columns in our data, but in order to build out star schemas, we're actually classifying tables as either a dimension or a fact. And so a dimension table is going to contain a key column that relates it back to the fact table, and then descriptive columns about that key. And so it can be, we talked about date already, so you can have a table, a dimension table that is, all the dates that you're working with in the date range of your data with a key. And then you can have further columns that are going to further describe those particular date references. Same things with maybe a product, a customer, an employee, just about anything. But any sort of descriptive information in the data that we're working with is going to become its own table in star schema. Whereas our fact tables are going to contain the key columns that relate to the dimension tables, and then our numeric measure columns. And as far as pros and cons go here, this is definitely the most optimized for what my practice does for reporting, particularly with regards to the Power Platform, but really for most other reporting platforms as well. These models are, some of this are simpler in terms of the number of tables with regards to with regards to what follows here in Snowflake. As far as cons go, if you're, we'll talk about this a little more when we get to Snowflake.
Looks like Corey might be lagging a little bit. But I think what he was getting to in terms of one of the things we'll get to in Snowflake is, as opposed to star schema, where in star schema, you might have multiple dimensions and that kind of aren't exactly like high in cardinality, and they could be duplicated in terms of the values within those dimensions at the different points in the star. This can really kind of be a pro and a con. It reduces like the overall complexity. Let me see if I can't get my screen up here with the PowerPoint as well. Sweet. I think this should be good. Sammy, do you want to pop in here really quick and just make sure, can you give me a heads up that this is visible for everyone? I will assume that's the case. Cool. So let me get to where we were. Sorry about this, everybody. Cool. So this is where we were. Yeah. So I think one of the things that you can kind of see, like when with the star schema in specific, is that you're always going to have the 5 points on the star. And I think the contrast will really be highlighted between that and Snowflake once I get to it. But when you kind of have these points on the stars, you can just kind of have it increased in sizes of the tables at the points of the star as you add more and more dimensions to those measure tables. That's what I think Corey was eventually going to allude into. If we go and make that comparison with the Snowflake schema, which is really the name comes from the kind of the complexity you see in a snowflake, that it has so much nuance in terms of its kind of different branches that from the center out it can make. What's really interesting is that the star schema is actually a special version of the Snowflake schema, which is why we had the conversation about presenting this versus presenting the star schema first. It's pretty interesting. So one of the things that might stand out to you immediately is despite still having with those orange ones kind of a star shape, you have an extension of the star which kind of forms that snowflake kind of model or image that you may have with those attribute tables. And the great part about that is that you can have each table have its own distinct attributes which can help further elaborate on certain measures and add additional conditions. What's really interesting is that this really keeps your tables small in size, so it reduces the storage requirement, but at the cost of potentially increasing the complexity. Because as the snowflake grows and grows in complexity and you have more and more and more branching, it really increases the burden of kind of digesting the overall data model. And it can increase the time it takes to really come up with exactly what you need to join on, because you have to digest more. There's just more nuance. Like you could potentially have, 6 or 7 attribute tables hooked onto one dimension table, and then have to use, the fact table to go and join with another one. So as the shape and the branches of the snowflake become more complex, it's easy to see how that can increase the development time once you have so much complexity. What's interesting is that really on the edges of the snowflake schema, you're gonna have multiple levels of relationships. Where in the star schema, each point in the star is really gonna contain those multiple relationships. Those multiple relationships in the case of the snowflake schema are going to be self-contained into the branches or the snowflaking and into those different attribute tables, so that those different levels of granularity are kept separate, which reduces the overall storage burden. But it, like I said, it also increases the complexity, because now you could have multiple different levels all skewed around one dimension. And it can make things significantly more complex. Some of the pros and cons. One of the things that you may see just in, on LinkedIn or on blog posts or, some types of social media, if you follow people who are in the industry, is that Snowflake has really become kind of a modern tool. And there's even like a self-claimed Snowflake database now. And it's not just a Snowflake schema. It's a database optimized for the Snowflake schema. And what's interesting is that really the Snowflake schema is really best suited for online analytics processing. And like I said, it also can increase or increase your storage savings. So you don't have to spend as much in terms of spend as much on your storage costs. Like I said, the one really major drawback I would say is the increased complexity. I think that can cause onboarding new people into kind of your data warehouse landscape to be more challenging. There's more nuance with each kind of edge of the graph, each edge of the snowflake, and as you have more and more and more snowflaking or more branching, you're going to have degradation in performance because you might have to perform more and more joins, even though it kind of gives you the ability to get at more specific information. It's at the cost of when you do need to get a broad swath of information from all over the snowflake. That can be incredibly complex and be and can really reduce the performance. Comping into something that's kind of yeah, what's up?
Thank you for rescuing me. My connection just completely dropped there. If you want to continue to drive, I think that's probably good until things stabilize here. But thank you, and yeah, man. It sounds like you've covered Snowflake well. Are we moving into denormalization now?
Yeah, but I think before we do that, it'd be just now that you're back, it'd be great if you could kind of, from your point of view, from the data visualization and BI perspective, what would you see are the major differences between working with a star schema and a Snowflake schema?
So when we're working in with reporting, and this is a good time, I guess, to talk about this. There's really sort of two aspects to data modeling. There's the point at which we're bringing the data into the platform and doing our ingests and transforms. And at that point, we've got a great deal of capacity to sort of shape and put the data into the structure that we want to be able to use. But then once we're done there, we load that data into the in-memory engine for the reporting so that we have the best performance, right? And in that side of things, we have a little bit more limited ability to relate, various tables. Certainly, the star schema is considered to be optimal at that point. Snowflake, because of its additional complexity at the edge of the graph, as you said, it gets a little fuzzier there, and the cardinality and the sort of direction of those relationships gets a little more difficult. And it's all stuff that can be solved for, but it ends up becoming a little bit of a performance issue if our Snowflake is really complicated. And so, best practices for reporting is, hopefully that you can sort of flatten the snowflakes down to single tables for a given class of dimension. That can have impacts where it ends up sort of blowing up the size of those dimension tables, right? And so you have trade-offs there. So you kind of have to look at the sort of what's best for the performance of your reporting. And really it sort of just depends on how big those dimension sets are, really.
Yeah, no, totally. I did want to point out, just as from a data science point of view, I think that there's some benefits that exist in terms of maybe doing just some analytics querying, or the fact that you can kind of around a dimension table have those really specific relationships and those different levels of granularity without necessarily storing it in the dimension table itself. Having those specific queries can make having the ability to do those specific queries rather than on a really large, immense point on the star, but just having kind of that small dimension table to one of the attribute tables in the Snowflake schema can be very performant and make kind of asking having like a dialogue with the data from like an analytics point of view very easy, right? Because now you don't necessarily have to understand like the multiple different kind of attributes within one dimension table already kind of pre-existing in the point of the star. Instead, you can be like, hey, let me just look at this one attribute in relation to the dimension table. Let me look at these two attributes in relation to the dimension table, right? And so I think there's some benefits there where you don't necessarily have to digest the entire, say you have like, you know, a dimension table in the star schema that has tons of attributes in it, right? And I know from talking, like working in with some of our clients, that they have some in a star schema model, some dimension tables that have, you know, hundreds of fields, right? And, you know, that can be a lot to digest as well. Like when you don't necessarily have each of those attributes into a separate table, you're really kind of increasing the burden of just kind of digesting everything that's in there and the different relationships of that one dimension table, you know? So it's pretty interesting. Like what is the right grouping condition? What's the right filter condition on one table? It can also be a little bit of a burden. But like you said, from a reporting point of view, having everything in one place can be great.
Yeah. And again, I absolutely. And I really appreciate you being able to sort of unpack this from the analytics and data science perspective for the people on the call. You know, I think with reporting, you know, the limiting factor there is almost always that, you know, users on interactive reporting are expecting to see, you know, really performant response to their clicks. You know, like, you know, if someone clicks on a pie chart on a report, not that we really like pie charts, but if someone clicks on one, they're going to expect to see this data almost instantly sliced by that particular, you know, cut. And so if you've got a really complex relationships with, you know, with a really deep Snowflake, that those performance issues are almost always going to end up being the limiting factor there.
Yeah, absolutely. And I think kind of those are kind of the two, I would argue, typical data models that, you know, most enterprise databases and open source databases really support. I think now that we're going to get into the denormalization, this one is really specific. And I think that there's only really some really specific databases out there that can support the denormalized schema to its maximum potential. One of those is BigQuery. And what's different from denormalized schema versus the star schema and the Snowflake schema is, rather than having this fact table in the middle and then these branches out either into a star or into a Snowflake, you're really kind of taking those disparate tables, which all have those relationships, and you're merging them down into one table, which stores multiple granularities. As you might imagine, that sounds like really complex from the outside looking in. But when done right and with the right database system, it can have some major improvements in terms of both performance and in terms of kind of having a one-stop shop for all the different use cases in one specific table. And the real prime example of when this is done absolutely perfectly is with Google Analytics. Google Analytics actually exports everything into one table in BigQuery. And in that one table, it is denormalized in the sense that for one session, which one row would be one session. And then within that row, you have multiple values. And you have to use some different data types to kind of really express that. But kind of breaking that down a little bit further, if we look at this bottom figure here, when we're transforming these different tables, these different fact and dimension tables into a denormalized schema, you can see that when you kind of go from the top down or from the left down, you're kind of going down from the highest granularity to the lowest granularity, right? So for one row here, R1, this is our unique, this is like our row in this case, and R2, this is our second row. So you can see that for this one row, you had different links here. You have 3 different links, these 3 forward in their values. You also can store the language, the code, and this isn't necessarily having multiple values for, like in this case, for forward, but you're kind of distinguishing using something like a struct or something else, or like an array, which would be like in this case here with links. You can have those different granularities all within one row. And when a database like BigQuery offers the tools to really work with these different data structures, it allows you to ask a wide range of questions from the same table, right? Your data model is really one table design. And I think one of the real benefits of that is when it's done right, you can answer everything from one table. When it's done wrong, or when the requirements are not necessarily known ahead of time, you can really have a lot of issues in terms of just constantly having to reconfigure it to answer those different questions, or, you know, because it could be, you know, really difficult to digest or, you know, express to analysts or BI people to exactly how they need to pull apart. And some of the BI tools might not necessarily have the capacity to work with the table in this manner, like unnesting an array or something to that effect. But from a performance perspective, removing the need to do relational joins because you're using a denormalized schema can increase your the time, or decrease the amount of time it takes for you to deliver something or do an analysis immensely. You no longer have to join, you know, hundreds of millions of rows together. Instead, you can maybe just have one massive table, and you can have those different granularities, and you can have aggregations exist in the same level or in the same table as the raw data. So it offers the ability to really have an awesome tool for a variety of use cases all in one place. I think if we look at some of the pros and cons, and this figure right here before we go into them, I think that's a great example of kind of showing that in one row, row 51, you have these different dimensions, and then you have a repeated value in event.status showing that in this case, it could be kind of like an Uber Eats or a DoorDash, right? Created, completed, picked up, driver found. So for one order, you can have the time, each time that each one of these statuses occurred, all within one row. So you don't have to necessarily have 4 different rows for this one order. Instead, you have one row and it contains all the information about one order. And it has all those different dimensions nested within that one row. And it shows the whole story of that order. So one of the real pros here, and I've kind of, you know, kind of gone on that for a while at this point, but is the ability to store those different granularities all in the same table. That can have that's a massive benefit. It also increases the performance for column-based storage, right? So BigQuery, as opposed to something like Postgres or, you know, Redshift or MySQL, it's column-based. So it's not, as opposed to being row-based like Redshift and Postgres and MySQL. What that means is that you really are, the columns, all the values are stored in a column manner rather than a row manner. So you don't have sort keys or anything like that. The filter conditions don't necessarily reduce the data that's going to be read. Instead, you read out entire columns. So when you're working in this manner, it can be super, super performant because things aren't stored together in one row, they're stored together in columns. And that's where you can get these huge performance gains with repeated values and whatnot. So there is one cost though, that if you just have a ton of one-to-many relationships within these types of these schemas, you can still have some performance degradation. Unnesting an array, and it kind of has to do like a Cartesian product or something like that, can still like really reduce the performance. But if you kind of have targeted that from the design point of view to make sure that you're still not going to have a ton of one-to-many relationships because you just stored those aggregations ahead of time, then that might not be as much of a con. It does have an increased storage cost because you're going to have these columns and values which have tons of repeated values in them. But that's because you're really gaining performance from the increased storage costs. So that's kind of a trade-off there. And it might not be ideal for the different reporting requirements when they're changing rapidly, right? I think that the denormalized schema is really when you kind of know all the use cases that you may potentially need to use with it, right? You could store all the metrics and different information you need for modeling or from a BI perspective, but you kind of have to have the foresight and the design of the data model from the onset for that to be really successful. And I think that you kind of have to accept that this table is going to report on certain things, and changing them is going to be a huge undertaking then after the fact, unless it's just minor changes. Corey, what do you think from your point of view?
Sam, this is awesome. Thank you. Are you guys able to hear me?
Mm-hmm.
Good. So obviously I've continued to have link trouble here. I apologize. Sam, I think, you and I have talked in depth about sort of this approach, just sort of, you remember when we were talking about trying to sort of come up with a sort of general purpose approach to pulling data on some of our engagements. Certainly there's challenges when we're looking at reporting with this, just because you're really having to take all these nested fields and everything and sort of expand it out. Most of the reporting platforms are not going to sort of natively work with this sort of nesting.
Yep.
And so but it's doable. And in terms of there being a flexible backend, to pull the data from, certainly this is definitely an option.
Yep.
And where it's Google BigQuery or something else, we can work with this. I think one of the things you and I talked about is that if we're pulling data in this, if our sort of data lake or our central repository, our single source of truth, is in this format, then we're going to end up having to do more work on the reporting side, which is not a showstopper. But it's just simply building out the pipelines and knowing what we need to do in order to work with this.
Totally.
You called out, on your cons list, my biggest thing, which is simply that, when we've got one big table like this, if reporting requirements change down the road, how flexible is this table schema going to be to, new metrics, new dimensions, down the road? And I think in a lot of cases, it's very flexible. But, it's, I think in terms of being forward-looking, that's sort of my big concern here with regards to building out the reporting pipelines, at least.
Totally. Yeah, I think that this one, I think from what's really the least flexible part of it is the highest level of dimension. So really what that row is going to be based on, if that's going to be changing in granularity, then this really that needs to be incredibly firm before you decide to go down this path, right? Like what you're determining to be a row ought not change, right? If it changes, then you're going to have to redo almost everything, right? You're going to have to redetermine exactly how you want what your repeated fields to be and what you want your different aggregations to be, and that all would need to be reprocessed and whatnot. But I do think there's like a middle ground, like what you're talking about, in terms of really you can stage this data in something in the middle that will make it easier for the reporting platforms to use, in the sense that you just have a materialized view on top of this, which is just kind of a tabular format that just pulls all that data out in a performant way, and then basically keeps that view up to date for the reporting side of things, right?
Right.
So, but yeah, I think that's a pretty good breakdown of denormalization. I know we've probably only got like 5 minutes left at this point due to some of the technical issues, but I know that you're an expert when it comes to the Power Platform, so I'm sure you can rattle through this real quick.
Are we on a hard stop?
I don't think so. I think that we can
so.
just kind of go as we want, but I know people might need to drop off if they've kind of dedicated time in their schedule for the 45 minutes.
Certainly. Well, yeah, guys. So, Sam, again, brings to this conversation a whole new level of perspective that I don't always have with regards to data pipelines, primarily for reporting. And I think he's given us just a really good look here at, what the possibilities are with some of these other schemas with regards, to other workloads and other tasks for the data. With regards to reporting, I did want to spend a little time unpacking a few other things here. So I think, when we talk about fact tables, it's worth talking about how we store that information. And a fact table is always, basically storing values that are going to be and should be summarized at various dimensional granularities, right? Values are always stored at the most granular level and then rolled up to higher levels of summarization at the time of the query. Measures that are going to be computed are going to have to be computed in the semantic layer of the reporting platform at the target summarization, because row level calculations are almost never useful in aggregate. And then I think there's a really good conversation, Sam, to be had here about, what is best practice for how we store our measures. Do we store them in a wide format where every measure's got its own column, or do we store them in a tall format, an unpivoted format where we've actually got the measure name is a further dimension on the data, and we've simply got a single single column for the values? I think there's real pros and cons to either approach. As far as with your workloads, do you have any sort of insight on that in terms of like which format you find to be most effective?
So I really just think it depends on the specific use case, right? I think that the advantage of, and just looking at this bottom diagram here, the advantage of having your measures, like in this case, the names of your measures are in this key column, and then the values related to those measures are in the value column. So cases, 745, population here. Storing those in the same can be a huge benefit when you only really care about, a few specific keys, right? Or a few specific measures. I also think that it can offer up the opportunity to kind of have like a cohesive kind of almost like a data store sense, where you can kind of just be like, hey, I want to pull this, that, and this other measure. Or you can have like these cool filter conditions on your measures because you gave them a common naming convention. And you can pull out like different swaths of, programmatically different swaths of measures from a table when it's in that tall format. So it offers just some different opportunities. I think the traditional way to work with it is always going to be in the wide format. And obviously a variety of tools in data science require that the data is in a wide format, right? But I think from just the ability for the unpivoted, the tall version to really kind of be pivoted out or, programmatically used for reporting has a lot of additional value from like it being that intermediary, the median, but before those different stages, right?
Right. And so, I think primarily where we've seen a lot of value in the tall format is where we're dealing with, we have data where we can't necessarily anticipate which measures or keys in this particular diagram are going to be necessarily presented depending on what cut of the data. You know, I'm thinking of some campaign performance reporting that we've done that was sort of below the fold, like smaller campaigns, and where we might not be able to completely anticipate what the reporting requirements would be for each of these campaigns. They might have different tactics, different channels, different, you know, and different measures as a result. And so being able to build out a data set that could accommodate that and a reporting approach, you know, using the key value as actually to drive our presentation of these metrics. And we would only then present, you know, what was there for a given campaign. You know, and so we wouldn't have a lot of dead screen real estate as a result, because we would, you know, we'd be only putting the measures on screen that were actually relevant to that, that were actually collected for that campaign. In which case, this data format is a really, it's a game changer. You know, but certainly I think for, you know, reporting engagements or reporting requirements where, you know, the metrics are known in advance and where the presentation needs to be tailored to a, you know, few specific key metrics, then I think definitely, you know, the wider format is going to be easier and more intuitive for most people to deal with.
Yeah, and I think the one of the big advantages is if you're like, you know, you just know there's going to be tons and tons of new measures added in the future as it expands, but the dimensions may remain the same. You don't need to like redefine the schema of your table. You can just insert new measures, right?
Right.
And you can insert them going all the way back to whatever granularity of your dimensions you need to do it, right? As long as they remain the same. So.
Yep. Exactly. And I think this segues nicely into the next slide, Sam, where, you know, we talk about one of the strengths of star schema for reporting is this idea that we can have multiple fact tables. And, you know, we were talking about a tall table that sort of could accommodate everything. If you're going to want to go with a wider table that has columns, you know, only for the relevant metrics, for all the relevant metrics, then I think we can look at multiple fact tables where, you know, you might want to separate out by, you know, channel or you know, data source, and where you've got data at one grain in one fact table or one set of metrics in one fact table, but you have, you know, another set of metrics or a different granularity in another. We can use, you know, sort of the capabilities of the star schema to allow for this. And so we can have measures from multiple fact tables. You know, they can be grouped, filtered, and calculated along any of the dimensions that these fact tables share. And this structure allows for a modularity and the ability to sort of integrate new measures from new data sources to existing reporting schemas without the need to completely reinvent the wheel. Certainly, you're going to have to go back and do a little bit of retooling, you know, to accommodate the new tables that you're bringing into the star schema, but it doesn't invalidate the old ones or the old logic, right? And so, and there's a lot we can do in the semantic layer with regards to solving for granularity mismatches. And so we can do things like align, you know, a quarterly budget, daily trend, things like that, you know, which is not necessarily rocket science, but it's nice to be able to store the data at the granularity that we actually have, rather than trying to sort of interpolate or sort of, you know, fudge it to make it fit. And so we can do things like that and effectively present without the need to sort of duplicate or otherwise manipulate the granularity of our source data.
Totally.
Awesome, man. In reporting, we in our data models, especially with regards to the Power Platform, we need to talk about cardinality. And cardinality is really the sort of the property of the relationship that determines the table type. We have things like, we have cardinalities that are one to many, or the inverse, many to one, There can be one-to-one, and we can do many-to-many relationships, but there are both logical and performance impacts with many-to-many. And so really, when we want the least ambiguity and the best performance, we try to structure our data so our dimension types always have one side of that relationship, and our facts are always going to have the many. And we definitely avoid, as we've talked, at all the other points through this conversation, we definitely avoid mixing the types together. And the fact tables, as we called out previously, each fact table should have the data that it contains loaded at a consistent grain, and we're going to handle granularity mismatches in our semantic model itself. I think, yeah, there we go. So when it comes to building out this stuff, particularly in the Power Platform, wanted to call out a few other things here. We've talked a lot about dimension tables, and really sort of how I wanted to sort of unpack a little bit how you can go about it in the Power Platform itself. The concept of a dimension table depends utterly on this idea of a surrogate key, which is a unique identifier added to a table to support this sort of data modeling. And by definition, that surrogate key is not defined or stored in the source data. And they're added to relational dimension tables to provide a unique identifier for each dimension table row. So what this means is really, if you had a column that was channel, say, and you had 10 distinct values in that column, you can extract those 10 distinct values into a separate table, and then we can assign an index to those values, and then join back to the source table that index value, and then end up removing the source column that was varchar, that was a text field, right? And so we've increased the efficiency of the fact table. It's no longer storing a big text field. It's now just storing an integer value. This ends up being more performant and also more efficient in terms of space. If we're in the case of a big database where you might have a long text key for a dimension, this can end up being a significant savings in terms of the size of the table. And this is something that can all be done, in the actual tool itself as we're extracting or loading data. Sam, we can move on to the next slide.
Sure.
Just revisiting the question of Snowflake, and we definitely covered this in the earlier conversation, but when reporting and sort of real-time reporting is sort of our paramount objective when we're looking for sort of that maximum response to a click on the interface. Multiple levels of Snowflake can really adversely impact the performance of the report. And so generally when we're talking about reporting, it makes better sense to sort of flatten a Snowflake hierarchy down to a single dim table. And in this figure, we have product category, and we have sorry, my screen is various levels of the product hierarchy in the upper figure, which are sort of snowflaked out, and below we've got that all flattened down into a single table, which ends up being a more performant. It certainly there's more work involved, and certainly that dim product table could get huge in the event of a large product hierarchy. But in terms of our reporting requirements, that's generally going to be more performant on the front end. Certainly keeping the data snowflaked on the back end is definitely a viable possibility if that's, especially if that's the way the data is delivered to you, or the way that, your backend tables are natively structured, we can solve for that on the front end. Thank you. I don't mean to be cruel to Anthony Michael Hall, but I felt like he was one of the stars in Weird Science and also Breakfast Club. Maybe you guys might be more familiar with that one. But I thought thought this was a hopefully fun representation of what slowly changing dimensions look like, right? So we've got Anthony Michael Hall as a teenager, and we've got him now. Same guy, just different versions of himself, right? And this is sort of the sort of idea behind slowly changing dimensions, where we might have the same members over time, but those members are going to change. So, for example, in a customer dimension, contact details might change, and we might want to keep the old values, but make sure that we are able to reference the different versions. This is probably more of an edge case for most reporting. Most of the time we're gonna just we're gonna have basically this type 1 SCD where we're just always gonna be presenting the latest values. But in some cases that's not right. And in some cases we need to support versioning of the dimension members. And in this case, that surrogate key that we talked about earlier is going to be different for the across the versions of a particular member, and we'll be able to reference them both, or however many there are. All right, Sam. Next slide. Role-playing dimensions. And here we've got the Incredibles, right? And some family role-playing the Incredibles, hopefully for Halloween. Hopefully this isn't something they do too frequently otherwise. But a role-playing dimension is a dimension that can filter related facts differently. And for an example, a date dimension table might have 3 relationships to a single fact table, where we might have order date, we might have ship date, or delivery date. On the front end, this is sometimes we only have one of those relationships active at a given point. So you can solve for this with either some sort of advanced logic in your actual measure. Give me the second, I've got an audio for this. Guys, I apologize. Hopefully that wasn't too big of an interruption. So like I was saying, we can solve by for this with either sort of some advanced logic in the actual formulas that we write with DAX in the Power Platform, or we can also solve for this by sort of duplicating the date tables and having one for order date, one for ship date, and one for delivery date. There's pros and cons to both approaches in reporting. And again, I think it's just something that's driven entirely by sort of what your reporting requirements are going to be. Just got a few more here, Sam. So junk dimensions end up being useful when we've got a number of dimensions with very few members in them each, sometimes even just one, and where we can combine them into a single table. And so we end up sort of consolidating many small dimensions into a single table, which is always sort of the Cartesian product of all the dimension attribute members. So if you've got 2 members in one dimension, 2 in another, and 5 in another, you're going to end up with 2 times 2 times 5, right? You're going to end up with 20 rows in that dimension table. But this helps us sort of keep the number of tables in the report down to in an effective minimum. And our girl here in this photo, she's wearing a dress made of recycled maps, it looks like. So again,
yeah, it's reducing a lot of information in the one dress.
exactly. This is another 80s movie reference. I don't know if you guys know Clueless, but it's sort of an 80s classic, and it seemed Clueless related to Factless, right? So next slide, Sam. So we use Factless fact tables when we need to relate really two dimensions that otherwise don't relate. And so a factless fact table doesn't include any measure columns. It only contains dimension keys. And you could use this to store observations, but at least in reporting, a more compelling use of this table structure is going to be to store relationships between dimensions. And it's really sort of the way that we can get around needing a many-to-many relationship. Instead, we can use factless fact tables as a bridging table where you can have, a dimension that has that is the one side of the many relationship relating to a table that has multiple rows for each one of those dimension IDs, and then that relating to another table that has multiple rows for another set of dimension IDs. And then we can use that bridging table as the filter for our fact. This is an effective strategy where many-to-many relationships are otherwise going to be problematic in terms of performance or sort of logical output. Next slide. So I really wanted to come up with a good picture for degenerate dimensions, but it just seemed problematic, right? No matter how I tried, I couldn't find a picture to pair with degenerate that just didn't seem like it was going to be offensive or upset somebody.
But then you did.
I thought about it, and then I came up with this guy. And, and again, another 80s, 90s reference. This guy's Andrew Dice Clay. Anybody remember him besides me? If you don't, he was sort of Jersey Shore before Jersey Shore. And he ended up becoming so offensive that his career sort of fell apart because people just refused to work with this guy. And I actually, a long time ago, took my best friend's sister to this guy's movie, not knowing what we were getting into. And it's really like, literally, I don't offend easy, but it was one of the only experiences in my life where I actually wanted to walk out of the movie, not so much because of myself, but just because I felt horrible about this girl I was with sitting through this awful movie. But anyway, Andrew Dice Clay likes to refer to other people as degenerate, so I figure we can refer to him as degenerate. And he needed to be filtered. He had no filter, and that's really what we use degenerate dimensions for. It's sort of where we've got a dimension that is really only useful for a single fact table, and it's sort of dimensional information on that data, and it's going to be necessary at some point for us to pull this out. But it's often where the dimensional members themselves, there's so many distinct values for that dimension that it really doesn't make sense to make it its own table. And so this is sort of a fuzzy exception to the rule that you don't want to mix fact and dimension tables. And it's where that value in that table is almost a measure itself, even though we can't really maybe sort of aggregate it in any sort of meaningful way. But this is something that you need to think really carefully about when you're sort of designing your data model. And that, guys, is really it as far as our discussion of data models for today. I did want to give you a couple of things quick as we wrap up. I mentioned, the close tie between data science and data visualization. Certainly at Softcrylic, all of our practices are closely tied to one another. We had a great conversation. It's about 25 minutes earlier in the summer where we all socially distanced, got together around a virtual poolside and sort of talked about the ways in which our various practices, sort of cross-pollinate and synergize and interoperate, whatever, words you want to use there. But this was a great discussion, and I hope that if we've piqued your interest at all today, that you guys will spend a few minutes listening to this and sort of just in order to sort of catch the vision for how various focus areas within the sort of broader spectrum of making data work come together. We've also got a couple of events upcoming on the calendar that I wanted to make sure you guys were aware of. Next slide, Sam. There we go. So next week, we've got 2 Microsoft-sponsored events that are great resources. They're free. They're day-long. They're hands-on labs. You can come away learning quite a bit. The first one is Analytics in a Day, which is heavily focused on Azure Synapse, which is Microsoft's new sort of single pane of glass management tool, all the way from Azure infrastructure all the way to Power BI reporting. It's a fantastic tool. If you're working in Azure, this is well worth your time to dive into. And then on the third, no, pardon me, I've got that backwards. So Analytics in a Day is on the 3rd. Dashboard in a Day is on the 1st. So on the 1st, we've got Dashboard in a Day, which is going to be an all-day sort of deep dive / overview of how to build out reporting start to finish in Power BI. We've been running this program for a while. It's been tremendously valuable to customers and also new friends alike, and certainly want to invite you to attend if you'd like.
Yeah, we also have another webinar on Friday, which will have myself, Brad Kosman, Josiah Martin, Brett Crawford, Morgan DePietro, and Vignesh. I will not attempt to pronounce his last name because it is very difficult. Don't want to do him that disservice, which will be about audience modeling. So be sure to join that if you have the opportunity on Friday.
Thanks, Sam. I'm sorry we didn't get that into the deck. Sam, do we have any questions from our attendees today that we should speak to?
No, we do not.
Okay, all right. Well, in that case, guys, I think we can wrap it up. The final slide here is just some further reading on the topics we've talked about today. I hope this has been a useful discussion for you all and that you've enjoyed it. And if you have further questions, by all means, there's some good reading here, but also feel free to reach out to any of us at the Softcrylic team. We'd love to hear from you. Thanks so much.
Absolutely. Yeah, have a great one, everyone.